Bueno, gracias a la gestión del licenciado Luis Rotaeche y el aporte de acá de Aponte, hoy tenemos acá como sorpresa, ¿no es cierto? Porque realmente fue insólito de un día para otro a Stuart Bradley. Bueno, nosotros le hicimos llegar a ustedes el currículum de él, ¿no es cierto? Lo tienen, ¿está? Entonces no voy a estar abundando sobre el currículum.
No.
Lo único que realmente sí es contarles un poco que realmente hacemos nosotros. En nuestro instituto estamos trabajando desde hace ya más de un par de años en todo lo que es la tecnología del oxidrógeno, en lo que es energías renovables, y estamos procurando, por otro lado, generar una diplomatura en energías renovables, pero no dedicado a la tecnología, sino al tema de la regulación y los costos, que es lo que realmente, digamos, no tenemos mucha experiencia en nuestro país. Y por consecuencia de esto, bueno, independientemente de lo que nos cuenta sobre la tecnología, a nosotros nos gustaría que nos convoquemos nosotros para discutir este tema. Estamos frente a un próximo gobierno, sea del color que fuere, que necesita respuestas que no tiene. Porque una cosa es la tecnología y otra es el manejo de todo el sistema de energía de nuestro país. ¿Está? Bueno, y bueno, no sé, Luis, si vos querés decir algo más.
No, just to welcome Stuart. We appreciate very much, and we are very interested to hear your comments and ideas about renewable energy. As Pablo said immediately, this year we start a new diploma. We are going to dictate a diploma in renewable energy. We care very much what you say. Thank all of them, because today is the eve of a very long weekend. So
yes.
Yes.
They
deserve a lot.
You'd rather not. Stuart, please, speak slowly. Because our English is not the best, you see. So
much better than
easy.
easy.
Fine.
No problem.
Okay, thank you.
Si hay alguna duda, sí que tienen de repente me paran y yo les traduzco las palabras acá.
Fine. Okay.
Okay. Well, first off, thank you very much for spending a good part of your holiday weekend to listen to me today. It's really appreciated. Thank you. And what I would like to talk about is some of the renewable energy trends in the UK and how that could affect Argentina and indeed other countries. But look at some of the technological, the commercial and the social aspects to the implementation of renewable energy in a country's energy supply. I work for the Energy Technology Institute. This is a partnership between
state-owned
and private companies.
Private enterprise.
So the private companies are two oil companies, Shell and BP, Rolls-Royce, okay, thank you. That's good. Caterpillar, Electricité de France, a utility company.
Mine is not working.
I just need to hold it.
Sorry, now yes.
We can leave a presentation here.
Sí.
Yes, I'll leave the presentation. No problem. We also have different government departments as well, including the EPSRC. Don't know what it stands for, but they fund universities. So we have universities, government departments, and then industrial conglomerates, international ones, of course. We also have a program associates called Hitachi, a Japanese company, and we're working with them on sustainable housing, on the smart grid, and on heating systems. Unlike here, we need heat rather than cooling. Some headlines of what our company does. We have £210 million worth of projects in process. We operate in 15...
100 million.
210 mil.
Yeah, 210 million.
210 millones. Sí, sí.
We operate in 15 countries around the world. So some of our partner companies are in the US, in France, Germany, Japan, China, India, but not yet Argentina. So let's hope for that in the future. We have 7 commercial products that have been launched already, and we expect to get to about 30 or 40 within the next 2 to 3 years. And by a commercial product, I mean something that is useful, that somebody can make useful to industry. Our aim is to build knowledge, so we invest money into things like bioenergy, marine energy, carbon capture and storage. Following on for that, we then develop the technology that we've learnt about. So for example, where we've learnt about something in the marine industry, we may make a subsequent investment to develop some technology. And then after that, we're also involved in demonstrating that technology and proving it. And that helps to de-risk and to encourage investment in industry. So, for example, if we take marine industry, we've invested in a test centre, and we'll do highly accelerated life testing and try to take away some of the risk for investors so that they can feel a little happier that their money is going to be spent on something productive and useful and reliable. We have well over 100 different project partners. Some of them are multinational companies such as IBM or General Electric. Caterpillar is one of our partners, of course. But we also have small companies as well, maybe 10, 12, 15 people. And we invest in those companies to help them bring their technology to market. Also in here you can see there's a number of universities that we deal directly with. So Cambridge University, Manchester, Strathclyde in Glasgow, Sheffield, and some in Europe as well. Aachen University in Germany, and 1 or 2 Danish universities. And what we're trying to do is to encourage close commercial links between the universities, the projects, and then for commercial exploitation. So we're trying to encourage those links and to exploit them and make sure that we help bring the full industry together. The background to all of our decisions comes from an energy systems modelling tool. So we have a suite of software tools that accurately model today's energy system, so supply through to demand, and also the conversion processes in between. And benchmarking from 2010, we then predict what the energy system mix could look like in 2020, 2030 and 2050. The reason that we go to 2050 is because we have a legal obligation to reduce our CO2 targets. And of course, unless we know where we're going, then we'll never meet it. So what we're trying to do is to plan the roadmap to meet those targets. The engineering tool, which we call ESME, has been developed by the Energy Technology Institute with two universities. The one that we're based at, which is Loughborough University, it's in the middle of the country, and also with Birmingham University. So there's both economical and technical parts that have input into that software. It's been peer reviewed, it's been thoroughly tested and backcast as well. So we've looked at what the energy system were doing in 1970, 1980 and so on, and just to make sure that it worked correctly for the back and for the forward. It's available to our members, so it's also used by government, it's used by Shell and BP, and they also add information to it so that it is up to date and includes things like the regulatory framework and government policy. Here's an example of a Sankey diagram which describes the UK energy mix in 2050. So this is one scenario that we see. Is it right if I I'm going to read from it. Okay, I can wave my arms. So we have the energy sources, and then the energy demands: buildings, industry, and transport. And then these are the conversion steps in between. So where we're converting from wind energy into heat, or into hydrogen, or geothermal heat into hydrogen, and so on. So you can see what we're doing is to convert a lot of waste heat that we would normally have into heating for buildings. This is something that's quite common in Scandinavia, where the temperature is very, very low, but less common in the UK. And you can see from this that we're principally going to take our electricity from wind, nuclear, geothermal heat, biomass, and a little bit of marine energy. Now that represents one scenario. And if any of the technology developments fail to meet their expected return or their targets, then we have other scenarios that we understand then have to take place for us to have to meet our legal obligations. So one of the scenarios is if nuclear doesn't happen, what energy source can take over? And in that case, then we think that biomass would be the next logical choice for us. There are some other options. We could use shale gas with carbon capture and storage, or we could use more marine energy, for example. So that's just one of the scenarios, and you'll be able to see some of these on our website as well. Okay, so we think that the first team is going to be, first off, that we would reduce electricity and heat demand. Our building stock is very old. 70% of the houses in the UK are over 100 years old. Some are badly maintained, and we need to properly reduce demand where we can. It's a very cheap
energy efficiency.
Absolutely. Okay. Energy efficiency. But also understanding when energy is needed, and when we can, when we need it in the morning and in the evening. We could have some forms of storage, for example. So if the wind blows at night, we can store that energy and then use it at the peak times. So that's all about demand management, and that's the part of the business that Hitachi is very keen on. Secondly, we are going to develop small nuclear. So that's generally speaking power stations of between 20 and 100 megawatts. We haven't got large rivers, so we're unable to use river water. But if we go to small modular reactors, then we can put them onto some of the smaller rivers that we have. I think.
Yes.
Well, your rivers
are
are all bigger.
We are developing 35
megawatts. Yeah. Actually, there's very good correlation between your needs and ours. It seems they're through different purposes, but we think the days of having a 5 gigawatt size power station are long over. Secondly, the other source would be fossil fuel. So again, that would be gas extraction from shale, hydraulic fracturing, but combined with carbon capture and storage. So if we look at a map of the UK, although we don't have a lot of space, we do have a lot of space underground in old coal mines, old salt mines, and of course gas and oil storage. So we can fill those with liquefied CO2. Fourthly, biomass, so farm waste, but also things that we grow specifically to burn. That's things like miscanthus, willow, other types of fast-growing biomass. Fifthly, offshore wind, and I'll talk about that one a bit more. Okay. Oh, just haven't done that too long. Here we go. The reason that we're interested in offshore wind, there's a very interesting statistic there in the bottom left. The population density of the UK is 255 people per square kilometre. For Argentina, it's 14. So there's a huge difference. We're a tiny little island, and we're all in at one end. So the only option that we've got now that all of our prime sites for onshore wind are full is to go offshore. So the effect of that is that we add cost because it's more difficult to build offshore wind. It's also more difficult to maintain it. But nevertheless, the wind is a lot stronger offshore. The average wind speed onshore in the UK is 4 metres per second, and offshore it's between 9 and 12. The other thing that changes is the capacity factor. So if we get 30% capacity, it wouldn't work. But offshore, we could get 50, 52, 55, somewhere around about there. So the ETI has invested in the development of floating wind in particular. So this is being developed specifically for water depths greater than 50 metres. And where we can put this resource very close to shore. So what we've looked at has been different types of floating foundation. We've looked at tether leg platforms, which is the development. You can see the picture there on the right-hand side. We've also looked at semi-submersible, and we've also looked at spar buoys. Now the spar buoy has been developed in Norway, and it's been worked on with. Yeah, and it's a long.
It's just a pipe.
Yeah, it's just a.
It's something like a pipe
with a weight on the end,
and
you tie it to the sea floor, and conventional turbine is on the top. So what we've done is to look at all of the different technologies that we could use to have floating wind as an economical choice. We think that the tether leg platform, which is on the right, is the best one. So this has an Alstom Haliade 150 machine. It's a 6 megawatt direct drive wind turbine we go to direct drive for reliability and also for mass distribution. And that will be installed at Wave Hub, which is a test site off the coast of Cornwall. It's about 26 kilometres from shore. The water depth is 58 metres. But more importantly, the significant wave height is 15 metres. Can you imagine a 15-metre wave? I mean, it's pretty significant. And this is it's very strong indeed. The Wave Hub site has been developed to produce wave generators. So that's where we will test marine energy. But there's a spare berth, so we're going to put this tether leg platform in place and thoroughly test it in the most demanding conditions that we could think of. So our aim is to very thoroughly test that technology. The average wind speed there is 9 metres per second, so it's a little lower than other parts of the North Sea. And the wind capacity factor, it's about 45–46%. Now, what that means is that we can reach a cost of energy in 2050 of about $110 per megawatt hour. That's in 2050 money.
Right.
It's in 2050 money. Yeah. So we've assumed inflation rates, we've assumed a capital cost rate of 10% or something like that. And it's useful to compare all of the different technologies to see which one is the most competitive and which we can see will carry on improving over the years while still meeting our legal targets. That cost is lower than nuclear and it's lower than using gas and CCS. So we think that
Gas at which price?
in 2050 we think that gas will be $135 per megawatt hour with CCS.
135
135.
megawatts dólares por megawatt.
Costo de generación. But what's the transfer price of the gas per megabtu? You are assuming for that scenario?
Yeah.
It should be over 10.
No, that's the reason I'm asking this exactly, because if you compare this number, what is happening right now, it is not convenient actually. It's our values. I mean, of course, if we compare with other values of the oil and gas price, it is another story. So perhaps
the other thing I need to add is that there's no subsidy on any of these technologies. So then, obviously, it's a political decision about which one gets the subsidy. But what we're trying to do is to have an even, a level playing field. Yeah.
Probably, yes, the price of gas should be higher than $10.
that's the scenario for this. I mean, we don't know the capital cost of this, of course, but anyway, we're talking about million BTU, price per million BTU, about $9–10 on this. And today is
6 for Argentina. In the mix of
Million BTU?
Yes.
$6?
Yes.
High.
No. This is the price of the mixture between domestic and imported. But if you want to have the price of Bolivia now is 7.
Well, after the presentation, I can get the
Sorry.
figures.
Yes,
and I can find them.
go ahead.
It's no problem. But just now, I don't want to tell you something that is wrong. I'll find the correct figures. Okay. What we also studied was the type of technology that the floating platform would need to use to get the lowest cost of energy. So we looked at current trends of technology, but we also invested money with some of the wind turbine generator makers and looked at their predicted costs with different scenarios. So we approached Alstom, Siemens, British Aerospace, a couple of the development companies as well that develop farms and then sell them as power stations. And looked at the predicted costs and the learning rates that we can expect. And what we concluded was that a upwind 3-blade direct drive generator of greater than 9 to 10 megawatts capacity was the full optimum size. And then for onshore wind, we would say 3 megawatts and lower with a conventional doubly fed induction generator and fully optimised structure would be the best for onshore. But nevertheless for offshore, 10 megawatts or so. So that then tells us where we needed to invest further money, because today a 10 megawatt design doesn't really exist. So we worked on the world's longest wind turbine blade. It's being manufactured and shipped to the UK for testing.
Which is the length of the blade?
And it's 100 metres long. 103 metres long, so a little bit extra. It was made in Louisiana by a company called Blade Dynamics, which is on it's on the NASA site in Louisiana, where they made parts for the space shuttle and so on. But they've got good knowledge of manufacturing with carbon fibre. So the internal parts of the blade are carbon fibre, and the aero shell is glass fibre. It's manufactured in 3 modules, and this gives us very simple tooling. It's modular tooling. It's a flexible manufacturing method, so we can swap between different designs for different manufacturers. And the 3 parts are joined together using adhesives, and a very clever adhesive on-site joint. So the intention is you take the 3 parts of the blade to site. There's an ISO container which has a controlled atmosphere, controlled temperature, and you make the joint. The other advantage of that is that it has much lower tooling costs. If you look at the cost of a mould to make a very large blade, maybe 70, 80 metres, it may be 50 to 60,000 US dollars. Whereas this manufacturing method is about 1/10 of the cost.
But on site with adhesives, does it mean you actually work in the sea, well, in a platform on the sea to stick it together?
Actually, it's on site. I mean, at the factory, which is and the factory to make these things is on the dock side.
Okay.
And then, because there's no transportation problems really by using a ship, but if you wanted to use a truck with 103 metres, that's a big problem.
On the shore,
you put the pieces together on the shore side and then take them offshore.
Yeah.
You join them in the shore side.
Yeah, we join them at the dock side.
With the ship.
Yep, exactly.
The ship.
You would still need a helicopter or a crane.
A crane, yeah.
Yeah, it's more expensive, just you have to do, just high cost.
Yeah, that's it.
Yeah, both.
The most difficult aspect is the handling of these parts. So being able to hold them safely if the wind is blowing and if the sea is moving along, if the wave heights are significant. The other aspect is health and safety. Somebody has to do the fasteners.
Screw.
Exactly. Yeah. The blade root is 4.2 metres diameter. So if you imagine the size of the blade root, it's enormous. 4.2. It's a huge piece of kit. Yeah.
It's almost this day, well,
Yeah.
almost.
Yeah.
In diameter. So.
In diameter, yeah. And rather amazingly, the blade is very lightweight.
Yeah.
It's only
Fiber, yeah.
I say only. It's only 20 tons. But if you compare against a conventional blade, it would be about 45 tons. So there's a significant weight saving. Now, of course, carbon fibre is an expensive material, but we need less of it. So what we see is there's actually a cost saving because it's lighter and your jigs and fixtures are lighter and the handling is actually easier as well, other than the length.
And the strength?
Have you thought
The
of
strength.
Right, yes, the strength.
Have you thought of graphene? Supposedly?
Yeah, we've thought about graphene for the 20 megawatt blade.
Aha!
20 mega.
20
20.
megawatt. Yeah.
I like it.
Yeah. And of course, if somebody says, can you buy me 30 tons of graphene?
They still don't exist.
No, it still doesn't exist. So we've got some way to go.
But I learned that I think in the UK there is a company who sells paint which already has graphene.
Yes, you're right. Yeah. The
Did you
supply
try
chain is starting right now, and the UK government has put £150 million into the first startup companies, and it's all for very, very light structures.
Yes.
Not semiconductors yet,
No.
but I think that will be the biggest market. It's an incredible material.
Yeah.
And we had the question on strength.
On strength. Ah, yes, of course.
Of course, strength.
The
Must be according to the wind.
Yeah, I can't think of it in terms of stiffness at the moment or strength, but natural frequency I can remember. The lowest natural frequency is 1.3 hertz. So that compares against 0.9 for glass fibre for the same size blade. So it's quite a lot stiffer, but lighter as well. So the two both help to get the natural frequency higher. Nevertheless, the deflection at the tip under full thrust is 8.5 metres.
Really? It's almost visible.
Oh yeah, it is. Yeah, it is visible. Yeah.
8 meters over 100. So
Yeah.
Crazy.
Crazy. And the deflection under generator short circuit is 16 metres. So when the generator short circuits, it's like a shock test.
Yeah.
And it will resonate. Yeah, exactly. Yeah, ring,
Vibrates.
Yeah.
Vibrates.
yes, and that's 16 metres.
Oh, when the generator short circuits,
Yeah.
it suddenly is free to rotate basically.
No, it's the opposite. It tries to stall it.
Oh, okay.
Yeah. So it almost tries to,
Yeah.
like stalling an engine on a car.
Yeah.
Yeah. Yeah. So you get a huge short circuit torque,
Yeah.
which is, it depends which type of generator, but the torque increase is a factor of 11. Yeah. So it has this big impact and then settles down very quickly. So in that case, of course, the structural damping is very important as well. So not just stiffness, but also the energy lost. We've also taken a look at leading edge erosion protection. This blade will rotate, the tip speed will be 100 metres per second. So it's a very, very fast tip speed. And so we have to put in some good leading edge protection. Otherwise the blade will just wear away.
100 meters.
100
Is
metres per second.
third is the third of sound speed.
Yeah. Yeah.
333.
Yeah, it is.
It's
Yeah.
a third of
But
sound of speed.
of course, we don't mind noise when it's 50 kilometres out at sea. Onshore, it's a big problem. Yeah, yeah. It's especially as we're a crowded island and the turbines are always close to
But
houses.
actually, the shadow cast by the wind is worse for people.
Yeah, absolutely.
That drives them crazy.
Yeah,
My brother-in-law has a windmill on his farm, and
yeah.
there has been even on television documentary of the neighbors complaining about him.
Oh,
So he was the bad guy because he suddenly put.
Not at my backyard.
Not
Not at my backyard.
that's right. Well, I've got a wind turbine which is about 1.2 kilometres from my house, and when we go for a walk, from village to village, and every now and again you think something's, that's the natural reaction. You think something's, the shadow goes across you, and you think something's falling.
Yeah.
Yeah, it is.
So
It's
that's-
much worse than the noise.
It drives people crazy.
It does, yeah. And also gives them back. So we worked on the leading edge erosion protection, and there's two ways to do that. The first one is using an abrasion resistant polymer, which is incorporated into the blade. And the second method is to use a very, very hard material, which is sprayed onto the polymer. This is called keranite, which sounds like something that Superman should be scared of, but it's aluminium, it's a phase of aluminium, and it is extremely hard, and that one's on test just now. And the other one is ice and salt protection. That's something else we have to be very aware of when operating out at sea. Similarly, if you have a wind turbine in Patagonia, then you would have to take care of other contaminants, volcanic ash, grit, sand, and so on. So similar problems. Okay, this is the cost profile as we see it in 2050. Just briefly, half of the cost is the turbine. The foundation, the turbine, the generator, the power converter, and so on. The rest of it is cost of finance, spares, labour, and insurance. Okay, so to conclude, we think that we could deploy 40 gigawatts of nominal capacity in shores around the UK. We think that the cost would be around about $110 per megawatt hour in 2059. Okay, there's a couple of questions here. What could it mean for Argentina? Because the technology that we're developing isn't specifically for the UK. There are other things that are spin-offs that are good for other countries as well. So there could be a chance for technology transfer to local makers. Right now it doesn't make sense to export towers and castings and things from one part of the country, or one part of the world to another. So we think that with collaboration with technology providers, that there's something for your local industry. That would mean that it would be quicker to market, and also that because you need a more robust turbine here, that there could be export potential to other difficult but valuable wind resources around the world. We think that would help to bring your cost of energy down as well, and also provide energy security and diversity. It's difficult to rely on one or two main sources of power, so that maybe this could help as well. So any questions on wind energy? I've got another bit on marine energy.
Now I have a question regarding the financing. When you say we are financing, who is we? The government?
No, this is the ETI.
And where do you get your money?
We get our money from the government,
Yeah.
Shell, BP, Caterpillar,
All those big ones.
Yeah.
And when you invest in those companies, are you getting a percentage on this business?
That's a good question as well. For the smaller companies, where there's maybe 10 or 15 people, we'll take a shareholding in the company, and that's partly to help protect them. If they're going to deal with, for example, the wind turbine blade company, it's only 80 people, and to deal with Siemens or General Electric, they need some.
Yeah.
They need some finance, they need some security, they also need some some assistance as well in technological matters. So then we call on engineers from Rolls-Royce or Shell or whatever, and they provide not only the cash but also some of the expertise.
Yeah.
And
Yeah.
you change that for a portion of the...
Of the profits.
No. You are a party, you're a shareholder.
We're a shareholder.
Accionista.
Yeah.
However, sometimes if the owners of the company don't want us as a shareholder, then we take a license, and that might be a,
Yeah, they pay a royalty fee.
it's a royalty fee. Yeah, that's right.
Or you can do a joint venture for a
Yeah, or
specific
we can
plant.
do a joint venture, exactly. With some of the smaller companies that have come to market with good technology, like energy storage, for example, then later on, some of the industrial partners have then invested in those companies separately. So, for example, Rolls-Royce bought into Tidal Generation Limited and invested in them, and they own them for 5-6 years. So there's lots of things to make it useful for the government and also for the industrial partners.
And when you mean collaboration with Argentina,
Mm-hmm.
would be collaboration with Argentinian companies who
Could be.
license the technology
Yeah, it could be.
and get the know-how, pay you, try to some things would be imported, some things would be done here.
Yes. There are lots of options with that. It could be that we are happy to license or to give away technology. It could be that if some small startup companies wanted capital, then we could invest in that. But it's the same sort of scenario as any of the US, European or UK companies that we invest in.
How did you compare your $110 per megawatt hour with Uruguay getting $64 megawatt hour?
That's in
But
today's
it's
money.
onshore,
This is
not
offshore.
offshore.
Of course, it's onshore and it's a big deal, international bidding, and they were able to get 64.
Yeah, actually the cost of onshore wind in the UK today is about $80. 80, but that's today's money, and that one is in 2050 money. So that's the difference. But we think that because the offshore wind speed and capacity factor is much higher, it offsets the difference in capital costs.
Could you tell us how much is this 110 in today's dollar?
Yeah, it's about 50.
50?
Yeah.
Okay. This is the...
That's the one you want to compare, isn't it? Yeah.
It's very difficult to look at the nominal figures, even for Argentinian people.
There's a lot of assumptions, of course, between now and 2050, and we may find in 5 years' time, 10 years' time, that there's another technology that is better. But we need to be ready with all of these different types of technology to make the correct decision when the time comes. We issued a paper 3-4 weeks ago which said to our government that you've got 10 years to decide which energy policy you're going to take. Because within the next 10 years there are decisions that need to be made, and that's the limit. Beyond that, and we're going to go into an unsecure situation where we will fail to meet our energy targets, and where we'll...
I think that
It could be.
it would help to understand your exposition if you put together the assumption on oil price.
Yes.
Especially when you say that this is better or lower
Yes,
than
yes.
the other. When you compare to gas, for example, as you did before,
Yeah.
it is useful.
Of course, don't forget that I'm also assuming that we'll need carbon capture and storage if we use oil.
Yeah, that's an extra cost.
Whether it's oil or gas or biomass, then we have to have carbon capture and storage.
What is difficult for me to understand and to see perhaps future here in Argentina is offshore energy. I mean, we are, I may say, absolutely opposite to the situation you have in the UK.
Yeah.
I don't see offshore wind energy in Argentina for the next.
Neither do I.
No.
Probably
Probably
never.
years.
Just never.
In fact, I
And
doubt
it makes no
that.
sense even to incorporate such technology, which is expensive, of course, in onshore when we have basically enough land and no constraints to go forward with conventional.
Absolutely agree. Absolutely.
It's not our problem.
It's not.
The problem is
No.
of Japan, Netherlands, UK,
Yeah.
right? But
Yeah,
not
small
Patagonia, Argentina.
islands that are- yeah, exactly. Yeah.
But
Yeah.
not for Patagonia.
No, not
it's
for
not for us.
No.
It's
No.
not for it.
You've got very strong wind resource here, and oftentimes it's in places where there's a low population density. So you could develop onshore wind turbines, which are 10 megawatts, and with 100 meters per second.
Right.
And then you'll have a lower cost than that, or you could have. I suspect there's going to be something else that will be needed to thought about when we're thinking of giant turbines like that on land.
Look, Stuart, let's see if I'm right. $2,000 per kilowatt inshore, and $4,500 for offshore. It's more than that doubles
It's
the price for each power unit.
actually in dollars.
Oh, well,
pounds.
dollar one.
Say it in pounds.
Yeah.
Okay, it's in our costing it is £1,800 per kilowatt for offshore, and it's 1,200 for onshore.
1.5 you said before.
1,000.
1,500 you said before.
Yeah, 1,500.
And 1,200.
Yeah, 1,500 and 1,200.
Dollar.
Just
Pounds.
20
pounds.
Not in
Pounds.
So
pounds.
it's just
Yes.
20% extra basically.
It's near to 2,000.
Yeah.
In dollars.
But this is the price
So
you
So you
see,
can say it's
Yeah.
$2,000 in dollars per kilowatt.
Stuart, this is the price you see for future, the future capex of this.
Yeah. I tell you what, can I show you the marine one? Because I think there's some
sure.
good information in this. Okay, so this is on marine energy. I'll rattle through this one because I think the figures that you need to see are a bit further down. Okay, so we considered 4 different sources. Tidal range, when you build a wall. Thank you. So that's a lagoon under a normal hydro turbine set into the wall. As the tide flows in, you get power. As the tide flows out, you get power. Then we've got tidal stream, which is in free flow. Wave energy, and then ocean thermal energy converters, OTEC. Absolutely no use for the UK, it's far too cold. So we looked at wave and tidal stream. Okay, here's the state of the nation as it is today. The marine energy is really quite new. There's a global deployment of only 60 megawatts total, of which 75% of that is in the UK. However, the resources are very, very significant when compared to the electricity demand. So we could commercially exploit 25% of our electricity could come from marine energy if the cost was right. So we're slightly ahead of international competitors. France and Canada are catching up. They've got very good resources as well. And we think that we can add research and development, engineering and services and supply chain. Probably not the nacelles themselves. There's our resource. So against the UK demand of 360 terawatt hours, 27% from tidal stream, wave could be 14%. The
360 terawatt hour
Yeah.
hour per year.
per year,
Yeah.
sorry, And there's the capex per power capacity in today's money. So that's in US dollars per kilowatts. It's very expensive. But when you consider there's probably only 12 of these machines made, you can understand why it's so expensive. All of this is on our website as well, so if you want the reports afterwards, I'll send an email with the links. Doesn't come up very well. I'm sorry about this, but I'll give you the copy of the presentation. It is clear on the presentation. So what the marine roadmap shows is the targets that we have to hit for marine energy to be competitive with other forms of energy. Okay? So we give a capex per unit of power, we give a target for operations and maintenance, and we give a target for capacity factor and availability. All of that rolls down into the levelised cost of energy. We set targets for that, 2020, 2030, and then out to 2050. From that, we can also tell which parts of the machine need most development, which is unreadable as well, but when you see the presentation, you'll see which areas need the most investment. That is the power takeoff, the method of installation, connection to shore, and the resource mapping. The government supports, UK Trade and Investment supports the development of marine energy. If we look at these strike prices, which is in pounds per megawatt hour, you can see that both tidal stream and wave are very generous, £305 per megawatt hour. So that's the price that the government will give to the wave or tidal farm developers over the planning period. That may be 10, 20 or 25 years. So they'll guarantee that price so that we can get investment into the industry. It's a subsidy. Mm-hmm. So right now, for example, 2015 to 16, the government is paying £155 for offshore wind, which is very, very generous. And that's how we're able to get such a lot of offshore wind capacity. Today we have 4 gigawatts of offshore wind.
And 155 in 2014-15 for the next 10, 20 years, or in that year?
Right, it's for the agreed investment period.
Okay.
This is the day that they first export power to the grid.
Yeah.
So if we go out to 2018, you can see it drops from 155 down to 140.
Yeah.
If you start on that date.
Yeah. Okay.
Is it true that this year in UK are having inaugurated the biggest offshore wind farm?
Yes, yes, it is true.
No.
Yes. The biggest offshore wind is at the London array.
100, 200
and
megawatts?
It's 460 megawatts.
460.
Yeah, it's big. It's Siemens 3.6 megawatt turbines, so they're quite small, but there's a lot of them. It was financed partly by the subsidy, the final strike price for renewables, the renewables obligation, and it's a power station, and it's owned by Masdar, which is an Arabian investment company, and it's owned by the Ontario Teachers Pension Fund. So it's got 2 owners. A bunch of Canadian teachers and an Arab sheikh. They've got lots of money.
Unbelievable combination.
Isn't it? It really is, yeah.
I could not imagine the Argentine Teachers Association financing this. No. We are a long way.
You should see what the university lecturers are buying now. Fusion reactors or something like that. So anyway, So the strike price is set for that period that's agreed at the start. So they'll agree with, the developers will agree with the government how long the subsidy is going to be. For certain sites, it's only 10 years. For the bigger ones, which are maybe riskier or they're further offshore, then they've gone for 20 years. Okay, where does the cost of energy come from in tidal? And there's a picture of a tidal stream turbine, and you can see that it is a waterproof wind turbine. There's blades, a gearbox, a permanent magnet generator, and at the back there's a little thruster that turns it around in the tide. And then there's a foundation. And the foundation that you can see on the right hand side is drilled pilings into the seabed, grouted in place, and it'll sit there happily in tide speeds between 3 and 8 metres per second. It's quite high tidal speed, and the best sites we've found are around the top of Scotland, where the water has to flow to fill the North Sea up. So it goes round that way, fills the North Sea up, and then comes back out again.
And it stays, you find the places where it stays constantly submerged.
Oh, yes, absolutely, yes.
There must be some tidal...
There is some tidal range,
yeah.
yes, you're absolutely right, yes. That Alstom turbine, the total tip height is 32 metres. It's quite a big machine.
Yeah.
But the water that it's in is 80.
Okay.
So even with some of the big waves and also the tidal range, which is about 2 metres, it's still submerged.
But
We hope.
what is 32 meters, the height?
To the tip, it's right from the seabed to the top of the blade, and it's in the 90-degree position, top dead centre.
It looks, for your next picture, I would recommend that you put something
A person.
To compare.
yeah, to compare a reference.
Like that.
You asked it, you
I
got
was
it. You asked it, you
That's
get it.
great.
unbelievable.
Okay, so that one is a wave energy converter.
Wow.
Okay, that's the Polaris machine. You'll see this all over the internet whenever anybody's talking about wave energy. And a Polaris machine is 4 of those modules linked together. And look at the size of it. It is huge. And effectively, it's a submarine.
Yeah, it's like
It's
submarine.
4 submarines.
So
Yeah,
what's
the
the
yellow
power?
submarine.
Right, that's a good question. Right, so it's one